Alrighty, so hey, by now you guys are becoming neuroscientists. You're getting a real clear idea of the brain, the various bits of it. Now, of course, all of this is introductory, and so will be what we're about to do. So let's actually just jump in. Brain Tour Part 1. For the next 2 lectures, what I'm going to do is give you a really quick tour around the brain, talking about some of the major sites, but also talking about some of the related phenomena as such, like lateralization and various other things. So we're going to talk about some of this to try to just kind of make you feel more comfortable with everything you're learning. Most of what I say today will be following what you've learned in the textbook, so I'll just try to reinforce it, with another perspective, so to speak. Please keep in mind that as you go through this chapter, you're learning a lot about a lot of different brain areas. As we go through subsequent chapters, we're going to come back to this. We're going to connect, like, for example, the next chapter we're going to cover, which will be chapter 5, by the way. We're going to skip over chapter 4. It's going to be about sensation perception. So we're going to talk about how the brain senses the external world, and we'll be connecting that to a lot of the things we're going to talk about today. Okay? But for now, here we are. Hop on our little sightseeing tour bus here, and we're just going to take a little bit of a tour around the brain and talk about some of the relevant issues and divisions, etc., as we go through. So, first of all, the first sort of way we can split things up, and that we often do split things up, is in terms of differentiating between the cortex, which is this sort of curly stuff you see here, and the midbrain, which are these structures in the middle of the brain. Now, the cerebellum is a bit of an oddball. We'll talk about the cerebellum, but the midbrain are most of these structures. We also talk about them as the limbic system, and that's the very old primitive part of the brain. And this very old primitive part of the brain really has a lot to do with survival. So if we actually kind of drop down to the second spot here, this contrasts with a number of more basic brain regions, which are more devoted to monitoring and controlling internal behaviors and automatic responses to external stimuli. This is, again, that very primitive part of the brain. It does things like make sure our heart is beating as it should be, that our blood is the temperature it should be, all that kind of stuff, that our body is the temperature it should be. It kicks in things like sweating when we get too hot. A lot of these basic instinctual kind of reactions that the body does to external stimuli. So it's absolutely critical to our survival. This is also, of course, where a lot of our emotion-based responses come from. So, when we talked about anxiety and issues with that, we talked about a lot about the limbic system and the role that it plays in that. Okay, so that's the more primitive brain region. We'll again revisit that throughout the course. For the rest of this, we're going to talk a little bit more about the actual cortex, the cerebral cortex, the area around the outside. And, the first thing, so this is the place where high-level perception of the world occurs, and where we get input from the world. It's also the place where we decide what to do with that input, and then output. We do things to the world, right? We manipulate the world. So yeah, we get input, but we also decide how we're going to behave. So in that sense, it's where all of our real controlled interactions with the external world occur. So we have these sort of automatic reactions to things, habitual reactions, that's more midbrain, and then we have the more controlled. And what do we mean by controlled? We usually mean behavior that's in line with goals that we have. We have certain goals, certain things we're trying to achieve, and when we talk about controlled behavior, it's behavior that brings us closer to our goals. We'll come again. We'll dance with that as we go through. Okay, but for now, let's just have the separation between the cortical regions and the midbrain. So, by the way, you notice that the cortical regions are very all kind of wrinkled up like that. Why? Well, there's a good reason. The brain likes to have a lot of surface area, but we've got the skull, and we need the skull is the protection for our brain. So whatever we want, if we want more surface area, we got to fit it into our skull. We don't want our skulls to become too big. That doesn't help during childbirth, and it's heavy, right? It's at the top of our head. If our skulls were too big, it would become a real problem. So instead, what happened with evolution is the brain found a way to take more surface area and put it into a smaller spot. So this takes up less area than that. right? But it's the same amount of actual tissue. It's just when you curve it that way, you can fit more into a space. And so that's what the brain is doing here. It's just fitting more tissue in. And that's why it's got that wrinkled kind of shape. Okay, now it turns out that these wrinkles are so-called the fissure. So we talk about the fissures and the gyruses. Fissures being these literal valleys, for lack of a better term, in the brain, and they tend to be pretty consistent. So if we took a few different brains out, a lot of these core fissures are in the same place. And that allows us to kind of think about the brain in parts, which is what we do. So again, the cerebellum's down here. We'll talk a little bit about the cerebellum separately, but the cerebellum mostly, just to give you a sense, it's really about taking our behaviors, our motion, whether it's like verbal behaviors or motor behaviors, but making them very fluid, making them very graceful. So if your cerebellum was damaged, you could still be able to move, you'd still be able to do things, but you do it in a very jerky kind of not graceful way. The cerebellum is what really fine-tunes our actions with the world, which is kind of interesting. But what we're mostly going to talk about now are these other four. In fact, in this lecture, we're going to talk mostly about these three: the occipital lobe, the temporal lobe here, the parietal lobe, sort of back top, and then we have the frontal lobe here, which includes the prefrontal cortex, that's the very front, but the whole area here we call the frontal lobe. So we'll be talking about each of these lobes. These three are going to handle input from the world of different sorts. In fact, let me give you a taste. Visual input, auditory input, and this will be input about sort of where our body is and where things are out in the world. We'll get there. But these are all going to do input so that we kind of understand what's out there. And then the frontal lobes are where that input is going to be combined with our goals. What are we trying to achieve? And then ultimately this will control our behavior, our output, what we actually choose to do within that environment. Okay, so we're going to kind of walk through, for now, these three lobes and talk about some of the issues along the way. And I think we're going to launch into some of those issues now. Yeah. Okay, so within each lobe, I will be talking about primary cortex versus association cortex. And so I just want to spend a little bit of time making that distinction clear to you now. Primary cortex is where the raw input from the world goes. Okay, so when you're looking at these red lines, this is really just a bunch of red lines, really. That's stimulating your eyes. And it's going to go back to your occipital lobe, which is at the very back of your head. But it's going to go to a very specific part of the occipital lobe first, right near the middle, something we're going to call primary visual cortex. That's the part where the raw input goes to. And so it's like first the brain says, okay, there's a bunch of lines out there. But then there's another part of the brain, the association cortex, that says, okay, but that probably makes sense somehow. What do we mean by makes sense? We're going to talk about this quite a bit in the next chapter. But what we mean is it fits with stuff I've seen before. It's probably just not a bunch of scrawled red lines. There's probably some meaning in those lines somewhere. And so the association cortex takes the input and compares it to things that it's seen before. It tries to analyze and recognize this input. Recognize. Let's take a moment with recognize. Recognize. Cog means to think, to sort of experience in your mind. So to cognize something is to have thought about it. To recognize something is to recognize it, to think of it again, to bring it back from memory, as it were. Okay, and that's what we mean when we recognize something. So when you look at this, my suspicion is you look at it and you almost immediately see the cat in the hat. You recognize this phrase. You recognize each of the words within that phrase. You've seen the cat in the hat before. You've seen all of these words before. But here's the important part I want you to realize. At the level of raw input, in fact, this letter is no different than this letter, or this one, or this one, or this one. And you see it most dramatically here in this last word, hat. Our association cortex makes us see that as H-A-T. In reality, the raw input is no different from those two. Why do we see it as an H in some situations and an A as in others? Because of this thing that wants to make sense. So when it comes across us, okay, that kind of looks like a T. Oh, what's that? Well, the next one's an E. What's most likely between a T and an E? Now, it could be an A, right? Taekwondo. But the is an extremely common word. And so the brain will naturally say, oh, if that's an H, then this makes sense. That's the. And this is C-O-C-A-T. C-A-T, I know that. That's cat. So now it suddenly wants to see that as an A in the. Okay, it sees that as a the. And now you've got the cat in the. Your brain's all ready to see hat. That's what it expects to see. And this is close enough. And if that means it has to see this as an H and that is an A, that's fine. Okay, so the core point here is there's the raw input that comes in, and then there's the part of the brain that's almost immediately, as we're getting that input, is trying to recognize what it is. That's the association cortex. And you're going to see in a couple situations that if you have damage to one or the other, you see very different sorts of symptomology. Okay, so let's keep that in mind. Let's also keep this in mind. Contralateral organization. The brain does this a lot, and you're going to hear about a number of examples of this. Now, what does it mean? Well, it means sometimes the left side of the brain controls the right side of the body or senses the right side of the body. And similarly, the right side of the brain is sort of in charge of the left side of the body. So why? Why does the right side of the world go to the left and the left side go to the right? I've never heard a good expression, a good explanation of that, of why our brain does this, but it does. And they're trying to show it here, where the left side of the body goes to the right side of the brain, the right side goes to the left side. You're going to see some examples of this when we talk about parietal lobe, for example, and when we talk about motor cortex, because it's output too. When you want your right arm to do so, that would be my left arm. If you want your left arm to do something, it's the right part of your brain that commands the left arm, and in fact, the whole left side of the body. The left side of the brain controls the right side of the body. Strange but true. I don't know why. I've never heard a good story, but it is true. So you're going to hear stories of that. Now, related to that, but a little different, is what we're going to call lateralization of function. So what do we mean by lateralization of function? Well, when we talk about the brain, we always talk about the frontal lobes, the parietal lobes, the occipital lobes, etc. And we talk about it like there's 4 lobes. But in reality, there's 8, because the brain has 2 almost symmetrical hemispheres, right? 2 sides of the brain, the left side and the right side. Now, there's a bundle of nerves in between these called the corpus callosum that connects these 2 sides of the brain and has them communicating instantaneously with each other. So the brain acts as a single brain. But in reality, there's 2 frontal lobes, one on the left, one on the right. 2 parietal lobes, this would be temporal, 2 temporal lobes, one on the left, one on the right. 2 parietal lobes, they're at the back, left and right, but also 2 occipital lobes, left and right. What we mean by lateralization is that sometimes the left half is doing something different than the right half. Okay, so you'll see examples of this as we go through, especially with the temporal lobes when we go through, and it seems like a sort of divide thing. Okay, we'll use the left to do this kind of work and the right to do that kind of work, and so we call that lateralization. You can go online. The colloquial way we think of this is, are you left-brained or right-brained? And we talk about right-brained people being creative, etc. Left-brained people being more analytic and strategic, etc. And people will say, well, which are you, more right brain dominant or left brain dominant? Again, for most cases, that's almost a silly question because your two sides of your brain interact so quickly that they act like a single brain anyway. But it's fun to think about. It's fun to kind of consider. And I actually mentioned one of my favorite albums in the world, Rush's Hemispheres, is inspired by all this and kind of, yeah, if you're interested, check it out. All right. So, you have these things vaguely. Let's get a little more specific. Let's start going into things. So let's start with the occipital lobe. So I wanted to just remind you here, remember that 3D brain thing? This is really good as you're going through these parts of the brain to kick it up. You can pull down the occipital lobe from here, spin the brain around, see it. Remember I said there's two occipital lobes? Well, there's one sort of on the left and there's one sort of on the right? So there are essentially two occipital lobes here. And yeah, you can go find out some more information about them, etc. Have some fun playing with the occipital lobes as you go through. We're going to do it just this way. So, but you can play that as well. Okay, so let's start with this occipital lobe. Back of the brain. Now, notice I say there's a little bit of vision also in the temporal lobe. We'll come back to that. But for the most part, the occipital lobe is where our processing of the visual world happens. So information comes from our eyes and goes right to the back of our brain and hits what we call primary visual cortex, that primary part of that cortex. This is, directly connected to sight. And if we have damage to that cortex, to that part of the brain where that image usually lands, what we end up with is something we call a scotoma, which is essentially a black spot. Like the person would be looking around and wherever they look, there's this black spot that follows them where they feel like I'm not seeing anything there. I'm just seeing black there. Because, that's, again, the primary input. And if that's damaged, you're not getting input into that. It turns out you kind of are, but you don't consciously feel like you are. You see a black spot that kind of follows you around. Okay, compared to association cortex. So this is where we'll see the split. So primary cortex, you're actually not getting the visual input. Association cortex, you are getting the visual input, but you're having trouble recognizing what you're seeing. So let me introduce you to this word because you're going to see it now and then, different variants of it. Agnosia. Ag is a lack of. Nosia is sort of knowledge. Agnosia means a lack of knowledge. And in this case, we're going to talk about visual agnosia, a lack of knowledge based on visual input. Okay, so let's tell you the story. This is from that Oliver Sacks. This is from that Oliver Sacks book that I talked about, The Man Who Mistook His Wife for a Hat. And it is the first story. Remember, I told you each chapter is a different story. Usually these are neuropsychology. So just to remind you, these are people who've had damage to their brain for some reason. And Oliver Sacks is telling you about the phenomenology that's produced. So in this person, they've had damage to their association cortex in the occipital lobe. They can see perfectly fine. They just have trouble recognizing what they're seeing. So in fact, in this title, what happens with this one character in one case is he's there talking to the doctor with his wife. The session is over and the guy gets up, and as is the norm at that time, the normal thing for the male to do would be to reach for the hat, which he wouldn't have been wearing while he was talking to the doctor, but to reach for the hat and then put it on his head as he leaves. Instead, this guy reached for his wife's head and grabbed his wife's head. So he mistook his wife for a hat. Okay, kind of weird. But it's not the only weird thing this guy does. In fact, a lot of people have this visual agnosia issue. And this is the example that I like the best. It kind of makes the clearest sense to me. In one example, they show one of these patients a glove, a leather glove. And the patient looks at it, and they're only allowed to see it. They're not allowed to touch it or anything like that. If they touched it, they might recognize it, right? But they're only allowed to see it. And so they show them the glove, and they say, you see this? And it's like, yep. Tell me what you see. And the person can describe the glove perfectly. They can see it. They have no trouble seeing it. It's not damage to their primary cortex, so they can see perfectly fine. When you then say, but what is it? Then they go, and they problem solve. They don't just recognize what it is. They instead go, that's kind of interesting. I don't know. Well, it's got like all these pouches in it, these little pouches. Maybe it's like a change purse where you can put different kinds of coins in each of those 5 pouches, and then you can take that change purse with you wherever you go. So they're trying to figure it out. Now, if you immediately hand it to them, they would take it and they'd go, oh my goodness, this is a glove. And then they would immediately recognize it and they would know what it's for. But based on visual information alone, they cannot recognize what they're seeing. They can see it, but they cannot recognize it. They have a lack of knowledge. And that's what the association cortex, it connects what we're seeing with what we've seen in the past. And that allows us to recognize things unless it's damaged. If that cortex is damaged, then we show this visual agnosia. Okay, so it's a nice example for talking about that distinction between primary and association cortex. That's there in all of the lobes, but really strongly present in visual. Okay, which is the occipital lobe. Okay, again, hop back on the bus. We're just going to go from spot to spot, just introducing you to these as you read about them too, starting to get yourself a little more comfortable with some of these terms and some of these parts of the brain. Okay, so let's go to the temporal lobe. The temporal lobe is sort of under the ear, which makes it easy to kind of think about because it is about audition sounds. Okay, it's about recognizing sounds that are out there. But this is where, so first of all, the primary cortex kind of tucks underneath. It's almost hidden from view if you could see the brain because it sort of tucks underneath. But again, if you damage the primary auditory cortex, those people can't hear certain things. Okay, it's the raw input again. And so there's certain sounds that they just don't hear. They can't hear. That's what happens when you get primary cortex, the raw input. You don't get that raw input. And so you're missing it. Okay, but what about association cortex now? Now that you're getting familiar with it, this is a case where we're going to see what we call laterality, brain laterality. Because what happens when you damage the association cortex? Well, that depends. The left brain or the right brain? Which association cortex are you damaging? Because we see different things in the case of the temporal lobe. We didn't with the occipital lobe. It's the same thing. Left or right, you have that visual agnosia. But here, it matters. So specifically, sorry, my Mac just keeps doing that when I don't know. I touched something the wrong way, so I apologize for the jumping slides. Okay, if you damage the left association cortex in the temporal lobe, trying to hit you with all these terms so that you feel comfortable with them, what you see are language issues. The left brain temporal lobe is really focused on language. And I mean, heck, language is a really, really important thing for us humans, right? That's our primary way of communicating with one another. And so it's a very important thing. And we've got we just kind of said, you know what, left temporal lobe, that's your thing. And so patients who have damage to this, we already kind of ran into the Broca's area, right? Which is almost more frontal temporal, but if they have damage to that area, they can't produce speech. That was Broca's area that we talked about. A little further back of the brain, there's an area called Wernicke's area, which if there's damage to that, then people have trouble understanding speech. They can speak perfectly fine, but when you speak to them, they don't understand what you said. This is also, by the way, the area often commonly hit by strokes. When people have a stroke, this part of the brain is often damaged, and that means they have trouble with language. So one of the big issues that someone, when they're having a stroke, one of their big problems is they can't tell anybody. They lose the ability to kind of explain what they're feeling. And so they end up being a little drifty. They know they're in trouble, and they'll often sort of go towards other human beings because they know they need help, but they can't tell those human beings they need help. And they're often feeling just kind of weird and whatever, and they can't use language. This is why it's really important. This will bring us to this other contralateral organization too. When people are having a stroke on their left side, and it's usually on the left side, what you see is a drooping of the face on the right side. The mouth kind of comes down, and the face in general kind of droops on the right side, which is the contralateral. The left brain affects the right side of the body. And when the left brain is having this trauma, it stops kind of controlling the right side of the body, and we see a bit of a paralysis or a drooping of the right side. So I say this all to you because, hey, it could save a life. If you have a family member ever sort of come up to you looking a little confused, acting weird, look at the right side of their face. If you see any drooping, get them to a hospital right away. The quicker you get them there, the less damage the stroke does. And it's all about time. So just keep that in mind. For this chapter, the important thing I want to highlight is, damage to the left produces these language problems. But what about right? What if you damage the right? It's not as common, but it happens. And when you damage the right side of the temporal lobe, then people lose the ability to comprehend non-speech sounds. So it's like the left side of the temporal lobe is focused on speech. The right side is focused on all other sort of sound information. And rhythm is a big one, right? Rhythm is a way of organizing sounds in a very structured way. And so the right side of the brain deals with those sorts of parts. This is why we sometimes say, the left side is analytic, words. The right side is artistic or creative, because it's dealing with the sounds that aren't words, the music, if we will, the rhythm, the beats. And so that's more right brain. And so if you see damage to that, then you see problems perceiving things like rhythms and such. So another, just an interesting case where we see this laterality, left side doing one thing, right side doing something else. Let me make one point while we're here on laterality. And we're going to connect this with whether you're left-handed or right-handed. If you are left-handed, then everything I just told you about laterality is less true. Left-handed people tend to have both in both brains. They have language and sound in the left and in the right. They are what we call less lateralized. Okay, they tend to share the duties across the two hemispheres. Whereas if you're right-handed, then you're more likely to do what I'm talking about. A right-handed person has language on the left, rhythm on the right. So the more right-handed you'll be, what's that mean? I'll tell you in a second. But the more right-handed you are, the more lateralized your brain is. If you're left-handed, it's the less lateralized. You don't flip. It is not the case that left-handed people have language in the right. They don't. Well, they have it in the right and the left. They don't completely flip where they have language in the right and rhythm in the left. That doesn't happen. A left-handed person has much more balance in how things are distributed across the two hemispheres. A right-handed person has less. And I said, well, if you're really right-handed, the question there is, imagine swinging a hammer in a nail, right? You have your dominant way of doing that. Imagine doing it with the other way. How horrible does that feel? If it's me, it feels really horrible. I am very right-handed. I really am a right-handed dominant person. And so I'm very, I have a lot of laterality going on there. Yeah. Sorry, weekend lectures. Let's go on. Temporal lobe. So we've done the occipital, vision, temporal, sound, and parietal. So parietal is an interesting one. So again, it's sort of the top of the brain near the back, over the occipital lobe, near the back of the brain. And this one's kind of interesting. So first of all, the primary sensory function involves perception of the body. Okay, so if there's something rubbing my arm over here, that goes to my parietal and it goes across my body. So it goes that contralateral organization. So my left stimulation of my left arm would lead to part of my right primary cortex getting active. If there was damage there to my primary sensory cortex in my parietal lobe, then there would be parts of my body that I didn't feel them if you touched them. I would have no sensation of feeling at all. Okay, so again, it's very much like primary cortex grabs the vision. Primary occipital lobe is where vision goes. Primary temporal lobe is where the sound goes, and primary parietal lobe is where the things that touch our body go, right? The feeling of sensations on our body goes to the sensory input. All right, primary. What about the association cortex in the parietal lobe? Well, here, once again, we see laterality. It depends on whether you talk about the left or the right. The left seems to deal with what we call proprioception. It's a little different here, but so proprioception is a really interesting thing. It's the ability to perceive where your body is at any point in time, where the various parts of your body are. So I can say for a moment right now, pay attention to your right big toe. You can do that. You can pay attention to your right big toe. You can kind of know where it is. Pay attention to your buttocks right now. What are you sitting on? How does it feel? You can kind of do that. You can move your attention around your body, and we kind of know where all the parts of our body are most of the time. Now, I'm going to say here, damage to this, when people have this damage, they lose a sense of where their body is. But we've all kind of experienced that. So have you done the following? Have you fallen asleep with your hand like this? You're sleeping, right? And you're sleeping too long, and all the blood drains out of your hand, and your hand is just laying there. And maybe at some point you wake up. You wake up and there's a hand there, and it freaks you out because once all the blood drains from your arm, you don't feel your arm anymore. It's like it's gone. So when you see that hand, it's like somebody else's hand at first, and you're like, what the heck? And maybe you realize, oh, that's my arm. And have you ever done this? Once you've done that, you got to go, and it weighs a ton, and you drop it beside you. And then the pins and needles start when the blood starts coming back in, etc. Okay? When the blood had all drained, when you were first there and the blood had all drained, you lose proprioception. It's like you can't feel your arm until the blood comes back into it. Well, that's what happens if you had damage to your association cortex. And one of the other stories in The Man Who Mistook His Wife for a Hat is a story of a woman that had this damage. And the story goes like this. It's just a nice, memorable one. She woke up in the middle of the night, and oh my goodness, there was a human leg in bed with her. Somebody had put a human leg in her bed. Imagine how disgusting that was. Like, ugh. And so she grabbed the leg and she threw it out of the bed with all her strength, threw that leg out of her bed. And then she went right after it. Problem? That was her leg. But just like your arm, she had lost all sense that was her leg. And it just seemed like a leg sitting there. And when she threw it off, of course, legs are heavy. And they tend to pull the rest of your body with them. So she went falling off after her own leg. That's a really important thing. So what's it really doing here? Well, it's kind of letting us know where our body is at all times. Why? Let's talk about what happens to the right side if you damage that. There's a very interesting phenomenon called spatial neglect. And so first of all, damage to the right parietal, you get this neglect of the left side of space. And it's really interesting. If you ask one of these patients to draw a clock, like an old analog clock with the numbers on it, they will go 1, 2, 3, 4, 5, 6, and they're pretty good. And then they kind of stop. They don't really draw the left side. And in fact, if you put a plate of food in front of them, they will eat all the food on the right side. And then if you spin the plate, they will then eat the rest of the food. But they won't until you spin it, because it's not that they can't see the left. They can. When you push them to pay attention to it, they can see it. But if you leave it to them, they neglect it. It's like they just don't attend to that side of space, which is weird. Okay, we don't completely understand neglect, but when we put these two together, this is the story that people often tell. The right side of the brain is about knowing where things are in the world. The left side of the parietal lobe is about knowing where our bodies are. And those two bits of information are important if we are going to move our bodies through the world. And when I teach in a classroom, the best example I give of this is, 500-seat lecture hall, and I will walk between the aisles as I'm lecturing. And that's a very thin space, and students have their bags and their winter jackets and all this other stuff, in between. And so as you walk through, you have to be very careful not to hit them, to scoot through. And so you have to know where things are in the world, but you also have to know where your body is in order to gracefully kind of go through that world. That's what the parietal lobe seems to be doing for us, kind of giving us a sense of where things are in the world and where our body is. And then when we decide to go moving through it, we have the information we need to get through. Okay, pretty quick so far. Occipital, temporal, parietal. You got some sense of these issues like laterality and like contralateral organization, and the distinction between primary and association cortex. So I hope all of that is good for you. You've heard a little bit of neuropsych. Maybe that's enough for this part of the tour. So we will stop the tour for now, except just to stress the following thing. The stuff you've heard about so far has been primarily the brain trying to take input from the world. And that's what these three lobes do. Occipital, visual input; temporal, sound; parietal, information about the world and our bodies. Okay? All of that to inform the frontal lobe, who will now decide what to do with all that and will take command of our body. That's what we'll talk about in the next one. All right. Thanks. Bye-bye.